Hi, I'm Elliott, CTO and co-founder of Neuralist, and today we'll be going over our Neuroevolution demo, which is demo number 4. And so, what is the Neuroevolution exactly? So, Neuroevolution is really a class of algorithms which allow us to evolve increasingly more fit models on a given data set over time. And the reason why this is so cool is the fact you can actually remove this entirely removes the need for the users to select and tune their own models. And this can sometimes come at the expense of time, but for smaller data sets, it really is not significant in terms of how much time it takes to evolve these models. Okay, so pretty much a couple cool things about Neuroevolution in Neuralist specifically is that a lot of Neuroevolution packages are really too dataset specific, or maybe they only involve one part of the data science pipeline, or have some other technical limitations that just simply make them not quite what we have in Neuralist. So what we do that's different from a lot of other packages, if not all the packages, is the fact that we evolve the entire data science pipeline. So that includes data pre-processing, feature scaling, and also the model hybrid parameters. So pretty much anything an ML, a machine learning engineer could think to do, that's not necessarily just model tuning can be essentially evolved. So how exactly do we use it? So really, it's as simple as entering the data set and letting Neuralist take care of the rest. It is indeed that's as simple as you can possibly have it, right? So what the user can do though to refine this is that they can control the number of generations that they can evolve for and how many chromosomes you have in each generation. And the chromosomes in this context really means how many candidate models you have, or really candidate data science pipelines to be even more specific, you have per generation. And you also can even prioritize which metric you want to evolve towards. So if you want a model that's better on precision, you can have that. If you want a model that's better on recall, you can have that. Essentially, we have a couple metrics you can prioritize the genetic algorithm to evolve, so it will evolve models which prioritize that given metric. So in this demo, we'll be talking about the CSV files again, so stuff like Iris and Bitcoin, that was in the CSV file format. And in that file, we essentially evolve gradient boosters or support vector machines for classification or regression problems. And in this demonstration, we'll be doing Iris again, but instead of focusing on just the data set itself, we're going to be focusing more on exploring the Neuroevolution tool set in its entirety. Okay, so the first part of the tutorial is really going to be very, very similar. Right? In fact, really exact to what we did in the demo one. So the only main difference here is the fact that instead of running Neuralist main, we're going to run geneticmodels.py, but we still do the same thing where we just type in -- path and type in the path to Iris. So we're going to go ahead and hit enter. Give it a second to okay, there we go. Finally responded to my command. Okay, so it's going to take a second to load in Iris, and we're going to do exactly the same thing we did in demo 1. It's going to print out the features like we see here. We're going to drop the ID like we did last time. Predict species. Okay, and now we're just going to let it run. So you see here what's happening is, so let's go over exactly what's happening. So here we have 20 generations max. We have 10 chromosomes per generation, and we see each chromosome has an associated fitness to it. And we see, looks like we actually, in first generation, we're able to actually evolve a great model. So normally this plot, of course, has some, has actual lines to it. It's essentially what this plot is supposed to be. It's essentially a plot of fitness as a function of generation. So essentially over time, you'll see that the number of generations of fitness will essentially, ideally go up to, as close to 1 as possible. So we actually normalize our fitness. So that means that the maximum fitness you can get for any model is always going to be 1. So the closer you are to 1, the closer to perfect fitness you get. So I'll close out of this plot for now because there's not much to show in this run because we simply found what we wanted to in the first generation. But that's what you want to expect. You're going to essentially get a plot of how the fitness increases or sometimes decreases a little bit. It increases over time. Okay, so let's scroll down to the bottom here. So generation 1 max accuracy 100%. So that means in this generation there was one model that had 100% accuracy. Let's see if we can find that model. It shouldn't be too challenging because there are only 10 of them. Let's see which one it is. I'm just going to scroll up until I find it. I think I found it. It's chromosome 2. So you see here on this chromosome, we actually managed to find a model that had perfect accuracy on train and test. No other model had that. So we were lucky enough the first generation, which is random, it actually was able to do it, which essentially means it's not too hard to do on Iris. But in general, on more complex data sets, it might take a few generations or even a couple dozen to a few hundred even to evolve good models. But ultimately, the genetic algorithm always evolved to prioritize better models over time. Okay, so we see, so here we have in the next line, after the generation 1 max accuracy, we also see that it's solved with a model of greater than 99% metric accuracy found. Let's break down what's going on here. So by default, without specifying, Neuralist evolves until you are greater than 99% accurate on your data. And this could also be even 99% F1, 0.99 F1 score, precision, recall, whatever. You actually can specify what your stopping criteria is. So what happens is Neuralist will, of course, go until generation 20 unless it meets the stopping criteria. So of course there's no need to evolve further if during a generation you have found the model you wanted to. So once it finds a model, or it evolves into a model that meets this criteria, that's the last generation. It'll stop evolving after that and store all the results. So that's what's happening here. And like I said, you can change this metric from accuracy to F1, to precision and recall, and it will evolve models that prioritize that. Of course, unfortunately, it only prints out test accuracy regardless of the metric. This will be something that's changed in the next update. And so that's really the basics of how this works. Let's just actually, before we actually run this again with a different set of parameters, let's just actually type in the variable that we want to talk about here, which is the models. So this is again a lot of things going on here, but essentially the models are going to be a dictionary like we saw in the image classification demo. So we're going to have, we just type in models.keys, and so we have models, fitness, and genomes. So if we do models, genomes actually have you can think of a genetic makeup of the model. So let's see here. So well, let's actually do it this way. Let's just look at one at a time. So notice that for the first genome, we have a gradient booster with a depth of 10. We have 50 estimators, which are 50 trees really, and here's our learning rate. And essentially, we have a scoring function. So essentially, there essentially are different scoring functions that the gradient booster uses to, there are different scoring functions that the preprocessor uses to determine which features get put into the model. So rather than training necessarily on using every single feature, it turns out that the Neuralist will actually figure out if all the features are even useful at all. Like we saw in the iris demo, if you guys remember, is that the petal length and petal width was actually far more important than the sepal length and sepal width. So Neuralist is actually able to pick up on that by itself. So actually it will throw out the features that something are important, or rather the chromosomes will consider that, and they will evolve models that only use a subset of the features. And you'll see here we have essentially feature scaling, and we didn't use feature scaling in this one, but in some of them you do. Let's go to the next model. Okay, so this is the one that actually performed well. Remember that the indexing in Python starts at 0. So the second model, which is the best performing one, as we saw up above. If we can scroll up and see if we can find it. We may not be able to find it. Well, maybe we can. Okay, here we go. So right here, 2. So we saw that 2 was the most fit. So that means index 1 should correspond to that model. So notice that the best model here was, had depth of 7, 385 estimators, and here are the parameters it uses. So notice that it actually feature scaled. So 0 to 1, so that means that all the iris features were scaled between 0 and 1, and then it also used, this criteria, the mutual info criteria, and then it also used a learning rate of 0.002 for the gradient boosters, and then these are the actual tree, the tree hyperparameters. And so you see here, this of course is not the prettiest display, but you can still look at the models and what was used for each chromosome. So So rather than you hard coding these models, you simply just had to hit run, and then and then there was a model that was perfectly accurate. So if we exit out of this, and this time let's do model SVM. So just like before, if we want to do SVMs, we can do either SVMs or gradient boosters, and we're going to essentially follow the same procedure we just did, but now it's going to evolve SVMs instead of gradient boosters. Okay, so we're gonna drop ID again. Predict species. Okay, now it's running through that. Okay, again, let's get found. First generation was able to find a 100% accurate model. So let's see if we can dig around and find that one. So that looks like it was the very first one. So that's the perfectly ideal case. So the very first model was able to get a test accuracy of 100% on the data set. And of course, some of the other models did not do as well, right? Some of the models actually have very poor performance. So we obviously, that's to be expected because they're randomly initialized. Okay, so And of course, one thing I want to talk about is the fitness function is going to be, it's not necessarily, the fitness here that we use is not necessarily just, well, it's not just the metric. It's going to be the metric plus the quote-unquote complexity of the model, and we use different criteria for that. And so it's essentially a combination of those two. The combination of the score we want to evolve for, and also the size and complexity of the model. So of course, more fit models are the ones which are both accurate and simple. That's essentially the way this fitness is approached. And the fitness is always going to be between 0 and 1, like I mentioned earlier in this demonstration. But that's really all there is to the neuroevolution. You simply just enter in a data set. Just remember, if you're going to do regression, you want to make sure you put mode, like something like, remember mode reg in the main part of the command prompt, not the debugger, and then you can just run that for regression, and it will essentially follow a very similar process, except the difference for regression is that we're essentially trying to find models which minimize the mean squared error loss. And essentially, but that's the criteria the regressor models use to evolve for. But that's really all there is to it. As long as you have a CSV file, as long as the columns have numeric data, which is whole numbers or decimals, that's fair game. You can essentially evolve that and see how you do. And the genetic algorithms that we use here are essentially they work in a lot of cases. There are special cases, I think, where they don't, even after a long time, they don't evolve perfect models. However, you still are far more likely to get a great model if you just use this versus trying to select the parameters yourself. But that's just sort of that's going to be very on a case-by-case basis, and of course time constraints matter a lot, but the tools are there. So I guess one last technical note, for those of you who are familiar with genetic algorithms, we use what's called an elitist selection. So essentially we keep, let's say, 2 or 3 out of the 10 chromosomes, and we throw out the weakest 7, and then we essentially we refill the population with 7 new random chromosomes, which again are data science pipelines, and we keep evolving that process over however many generations, or until we reach the stopping criteria. So that's essentially how that works. So for those of you who are interested in the technical details. Okay, all right. So I hope you guys enjoyed this introduction to neuroevolution with Neuralist, and we'll see you guys in the next demo.